You're all awake. I'm very happy to see so many faces. And first of all, congrats for being here. It's early, I know. It's 8 o'clock, and you're sitting here. I appreciate that a lot. My name is Maarten. I work at a Dutch company called InfoSupport. We have a booth up there. I'm not going to tell you you should go there and ask for a job, because that's not why you are here today. And that's not why I am here today. I'm here to tell you about secure sockets layer or transport layer security. And all the rest we can discuss later. But if you might have any questions, which we cannot discuss after the session because we have a keynote and an opening and stuff, just find me somewhere at the conference. I might be at the booth, I might be walking around or just visiting other sessions. Or you can find me on Twitter. The hashtag is down there, username. So let's get started. First of all, just quick raise of hands. Who recognizes stack traces like these? And when you see them, what do you do typically? Get coffee. That's always a good one. Should have done that too. Any other suggestions? What do you do? Find somebody who understands. Thank you. That's exactly the answer I was hoping for. I used to do that a lot too, I have to admit. Because, well, it can be rather frightening, right? I mean, the error message is a bit cryptic, and you're not completely sure what to do. What does it actually mean? A path building failure? What's going on? Well, by the end of this session, you might not be an expert, but at least you know where to start and what tools you can use and what is actually the stuff that you're using. So, let's go. First of all, before we dive in, just to stress that it's important that we discuss all of this. People often ask me, why do you actually care about this stuff? It's boring, we use it every day. It's just there and it works, right? And if it doesn't work, well, we go to this one colleague who does understand and can fix it for us. Well, first of all, as you might have experienced yourself, it's pretty hard to set up transport layer security correctly. It's even harder to understand what it is and how it works. But on the other hand, it's crucial for secure connections between systems. And the systems that we're building are more and more connected to each other. Especially if you're joining the microservices hype, you're building maybe tens or 20 or hundreds of systems, and they are all connected to each other, and each of them needs to have a secure and reliable channel to talk to the other systems. And we're building many of these systems, and these systems also communicate with each other, and we deploy them to clouds because, well, we just prefer to use someone else's computer instead of setting up our own. And that means that we also have connections that span the whole globe. I've seen a project where for a simple transaction, data was flowing from the Netherlands to Singapore and back. Well, all of this needs to be secure, obviously. And if we do not understand what it is and how to set it up correctly, we can easily make mistakes which can lead to big failures or even worse, loss of money or loss of trust by our clients. So it is important. You might have seen this model before, the OSI model. Who's familiar with this 7 layers? Oh, wow, that's awesome. Great. And if you look at this model, you can see that it says, well, here's a presentation layer, and the presentation layer says, well, that's where we do encryption. So if an application needs to securely transfer information to another system, well, the application should basically do that itself. There's a presentation layer, and, well, that's not really part of the operating system stack. Meaning that if we do this, all our applications need to reinvent the same wheel over and over again. And we as developers are building encryption, which is cool to build, but also very hard to build and easy to do wrong. Now, what is transport layer security? It's nothing more and nothing less than moving this responsibility of encrypting data a few layers down to the transport layer. What does that mean in practice? It means that we have a transport, a TCP connection, which is secure by default. That is, if we set it up correctly. Quick history then. It all started with SSL 1.0, which was described by Netscape, a predecessor of what is now called the Mozilla Foundation. But they never released it because it was, well, it was basically terrible by design. It wasn't secure by design, it was terrible by design. So they never released it. SSL 2.0 fixed most of the issues that were in the never released SSL 1.0, and it was released in 1995. Well, as for me, I was in primary school then. Don't know about you, but that goes way back. But since 2011, you can't use SSL 2.0 anymore. POODLE was then published. It was an attack that basically proved SSL 2.0 is not secure anymore, not at all. The same holds for SSL 3.0, which was released in 1996, and a few years later than SSL 2.0 was also proven to be vulnerable to the POODLE attack. So don't use any SSL anymore, please. Then, in 1999, TLS 1.0 came out. Wow, cute. SSL 1.0 came out, which was basically roughly the same as SSL 3.0. There were a few minor differences. Yeah, we have a picture again, thanks. That's great. SSL 3.0, TLS 1.0 came out basically the same as SSL 3.0, a few minor tweaks, but enough for the IETF to give it a new name. It was also proven vulnerable, but to a different attack in 2011. This attack was called the Beast attack, and since that attack was published, don't use TLS 1.0 anymore. TLS 1.1, TLS 1.2 came out later in 2006, 2008, and this very summer, 2018, which is 10 years later than TLS 1.2, we had TLS 1.3. So what should you use? Well, generally, I would advise to go for at least TLS 1.1 because it's not yet proven to be broken. That's not the same as it's secure, as you might understand. There's no one who has made publicly that he can crack it. But maybe someone can, and we just don't know. But if you have the option, go for newer versions like TLS 1.2 or TLS 1.3. Maven Central switched to TLS 1.2 earlier this year. I think it was spring. Caused a lot of troubles for people running build servers on older versions of Java. But, well, basically, if even Maven Central allows themselves to upgrade, well, maybe it's a safe choice by now. So, let's see. Transport layer security. What are we actually targeting here? And to do that, we have a quick demo, which is there. Yep. On my machine, I have a web server, a very basic web server, and I have a packet sniffer. And a packet sniffer is running in this window, is a tool that will inspect all traffic that comes through my network interface. So, now I'm using CURL, and I'm going to visit my own website, which runs on port 9000. And as you can see, it spits out lorem ipsum and the rest, which is not really interesting text, obviously, but at least it tells us that the web server is alive and gives us some data. But now the thing is, my packet sniffer, as I said, it will inspect all network traffic on my network card, is able, well, it just shows those very bytes coming over the line. HTTP 1.0, okay, HTTP 1.1, 200, okay, lorem ipsum and the rest. So what this says is, if someone is able to inspect your network traffic, and this can be because you are as an attacker on the same machine, but it can also be because you are, for example, able to inspect network traffic because you're on an open Wi-Fi, just saying. If your target victim does not use a secure website, you as an attacker can read along because the network traffic isn't encrypted. Now for lorem ipsum, this is not really a problem. But you can imagine if this was my internet banking system, I wouldn't be a very happy customer today. And I would probably leave the bank and go for another one, which hopefully does their stuff better. So that's the issue that we're trying to prevent. And if we want to prevent that, we need three things. And that's basically the remainder of this talk. First of all, we need public-private key encryption. Secondly, we need certificates that tell something about the key possession of the server that we're talking to. And finally, we need parties that can sign certificates, certificate authorities. So, public-private key encryption as a first. It's tough materials. I could talk for maybe 2 hours or maybe a day even about how RSA works. It's very technical. You need to understand a lot of math. I don't hold a PhD in math, and I think neither do you. So I have a simpler language to describe this. I think this is a language that we all understand. At least I hope so. People in the back, can you still read the diagrams? Great, thank you. So what do we see here? There's a safe, and the safe has two locks. Now this is a very special safe, because there's one key with a globe on it. This is what we call the public key. And there's one safe with my face on it. This is not a public key, this is a private key. And the two of them are related to each other in a mathematical way. Now what happens if I use the public key? I can trigger the lock one direction. If I use the private key, I can trigger the lock the other direction. And this is very interesting, which we'll see in a minute. So what am I doing? I'm keeping the key with my face on it to myself. It's in my pocket and you're not going to have it. But I can give my public key to each and every one of you. You're free to have it. You can have 3 copies if you want. It's no problem at all, because it's public. Now, suppose someone of you wants to send me a letter. Can be a love letter, I appreciate that, but it doesn't have to be a love letter, can also be a rant. What you do, you write the letter, you put it in this special safe. And using the public key that you have, you close the safe. The safe is now locked. And as we saw in the previous picture, the lock can only be turned the other direction by the private key, the key that I have, and you do not. So what can we do? We can put the safe on a transport, and it can basically be any transport. This is just a regular truck. You could use pigeons, you could use radio signals. It doesn't really matter, because anyone who is able to intercept the traffic will not be able to open the lock, unless using dynamite, maybe, but that's a bit out of the scope of this presentation. So the safe is there, it's driven by truck to me, and since I am the very only person who has the private key, I'm the only one who is able to open the safe, get the letter out of it, and be happy with the message that I received from you. Well, this is obviously not the real stuff. The real stuff is just a lot of math, and we're not going to cover all of it, but just to give you a basic idea of how that works. The very first step is that we select 2 prime numbers. Let's call them P and Q. And the only requirement is that they are positive and that they are a prime number. Well, the demo gods are not with me today. Let's hope. Anyway, the second thing that we do is we calculate a number that we call the modulo. This is not the mathematical operator modulo, this is just a number that we call the modulo, and it is calculated by multiplying P and Q with each other. P was 11, Q was 17, P times Q is 187. Next thing we do, we select one random number, can be any number as long as it is above 0 and below the number that we have just calculated. So let's just say E is, well, the number 3. Doesn't really matter, any number would do, as long as you cannot predict it. And now I'm giving you a small mathematical question. Can you please find me a number D for which this equation holds D multiplied with E minus 1 modulo P minus 1 times Q minus 1 equals 0. So if I divide the left hand by the right side, I don't want to have any rest number, must be an integer number. Well, as we see, this is an equation with one unknown, and as we learned on secondary school, if I'm not mistaken, this can be solved. And I'm not going to take you through all the steps. For those who like, you can verify that it's correct. What we see is that we end up with a number D that is 107. So if I would fill in this equation, D is 107, I would have 107 multiplied with 3 minus 1 modulo 11 minus 1 times 17 minus 1, which equals 0. Great, equation solved. Now move on. Just a quick reminder, if I would not have selected E equals 3, but E equals, for example, 75, I would have found a different number D, and this is a very important thing to remember. This random number really does matter. Now, let's just do a quick a quick experiment. What if I do not tell you the values of P and Q? I'm just telling you P multiplied with Q equals 299. Oh, and by the way, the random number E, is 5. And once again, could you please find me number D? Now we have an equation with 3 unknowns. And as we also learned on secondary school, it's not easily solvable, or maybe it's even impossible to solve, depending on how hard the mathematics are. Let's just assume it's pretty hard. The thing is, the bigger the numbers are, the harder it becomes. But again, if we do know P and Q, it's trivial to do the same mathematical equations again over and over, and we will find D equals 317. And I'm saying trivial because for a computer, this is truly trivial. It's a no-brainer. Now, as I said, the bigger P and Q are and the bigger their product is, the harder it becomes to solve this equation with 3 unknowns. You can do trial and error for small numbers of P and Q, but the bigger the numbers are, the harder this becomes, and you will need more and more calculation power. You'll need graphical video cards to solve this, and eventually you'll find yourself in a situation where you can't do it anymore. So what we do, we select very high numbers of P and Q, and we do not distribute them, but we do distribute their product. And we also distribute the random number. This is the public key. The private key are the individual values of P and Q, and I'm keeping those to myself. And that brings us to the application. How can we actually use this mathematical tricks to encrypt and decrypt stuff? Let's just say that we have a letter that starts, a message that starts with the letter G. Well, we're just using a normal Latin alphabet, so G is the 7th letter, so we have a simple code table where A is 1, B is 2, C is 3, etc., G is 7. P times Q, as we saw, is 187. The number E that we have selected is still 3, and the letter G is the number 7. We calculate 7 to the power of E, which equals 7 to the power of 3, which equals 343. We calculate that number modulo 187, which is 156. 156 is our encrypted message, and without knowing P and Q, the individual values, it will be, again, very hard to figure out what the original number was. But since we know P and Q because we hold the private key, we can derive D, which is 107, as we earlier saw, and we'll do a different equation. We'll calculate 156 to the power of D, which equals approximately 4 times 6 with 234 zeros. That's a rather big number. Your smartphone calculator app will not do this. My Mac calculator app will not do this. Excel will not do this, but your computer has a very powerful CPU. And once again, for the CPU, it's peanuts. This is trivial. It can easily calculate very big numbers that go even beyond what we can easily describe. Now, if we do a modulo again with 187, we find the number 7, which was the letter G. So since we have this value of 107, we can find out what the original message was. The original message was 7. And we have a code table that says 7 equals a letter G. So we have a circle now. We have decrypted the message that somebody else encrypted. And the only way we could decrypt it was because we have the private keys for this. Any questions so far? Just raise your hand or shout. Ooh. Well, great. We'll continue. We're not continuing with fairy tales here. Definitely no time. So, if two systems want to use this mechanism to negotiate a secure connection, they go through a few steps. It all starts with a client that tells to another system, to a server, hey, hello, I want to have a connection with you. The server will say, well, okay, that's fine. Here's my certificate. And in a few minutes, we'll see what a certificate is. If the certificate does not contain enough key security materials yet, it will send an additional message, which is the server key exchange, and it will then say, well, I'm done with the hello phase, with the handshaking phase. The client will in return send a client key exchange message, which contains also cryptographic materials, and then line number 7 is very important. It sends a change cipherspec message, which basically says, everything I'm going to send to you from now on will be encrypted using the key materials that we have exchanged so far. The funny thing, by the way, is that although the server sends their public key to the client, and the client sends their public key to the server, what they will be using in the end is a randomly generated temporary symmetric key. What we've seen so far are called asymmetric keys because both parties do not have the same key materials. I have the private key, you have the public key. Symmetric encryption is where we both have the same key. And it's mathematically easier for the computers to calculate the mathematical stuff that is needed to do that. So what they do is they generate a temporary key just for this session and use that from then on, just because it's more efficient. But as I said, the change cipherspec there, line number 7, everything I'm sending to you from now on is encrypted using this temporary key that we have just generated using our corresponding public-private key pairs as base. And we're finished now, and the server will reply with a change cipherspec message, and it will say, okay, well, if you're going to send encrypted stuff, I'm going to send encrypted stuff as well, using the same key materials that we have just discussed. Great, thanks, and let's continue the conversation. The handshake is now officially finished. And from that moment on, we will see in a few seconds, it's not possible for a man in the middle, an attacker, to intercept the traffic and also understand the traffic. So, quick demo once again. Here's my packet sniffer again. I'm now going to visit a different website on my same machine as well, which is running HTTPS. This is what you see every day in your web browser, right? And runs on a different port. It will still tell us lorem ipsum and the rest because it basically serves the same content. But now, look at the packet sniffer. Is there anyone who can make sense out of this? No, you cannot. This is the transport layer encryption in action. This is where the transport layer is encrypting each and every byte that goes over the wire, just to make sure that no one who is in between can actually read or understand the traffic. And as you can see, also if we scroll back a little bit, there's nothing here what we can understand anymore. So this is what your bank does. This is what the web services do that you consume in your day-to-day work. They make sure that someone who is sitting in between and is able to intercept network traffic will not be able to actually read along and sniff data. So, we've seen the first thing, we've seen how public-private key encryption works. Now we can dive into certificates. A certificate. I think many of you actually have a certificate. You have a driver's license. Or if you don't have a driver's license, you have a certificate from your high school that says you are graduated in some sense. And a digital certificate is very similar to that. It's a digital document that says something about somebody else. My driver's license says about me that I am capable of driving a car. Some people beg to differ, but well, some time ago it was considered a good idea to give me a driving license. There's a signature on the driving license so that anyone can verify that it's genuine, and there's also other genuine marks like the watermark and stuff. A digital certificate obviously does not have a watermark and a picture on it, but it has a few other things. It has a subject, so that's about who are we talking? Well, we are talking about, for example, www.google.com. That's a subject. We have a validity, just like a driver's license. It's not perpetual. It will someday it will stop being valid. it says what it can be used for. In my case, it says you can drive a regular car, but you are not allowed to drive a truck or a bus or a motorbike. And in the same sense, a digital certificate will say, well, this certificate can be used to secure web traffic, but it's not able to be used for client authentication, as an example. Then there's a public key, and that's the interesting part. That's the public key that I own. So if I would present you a digital certificate, it would say, Maarten has this public key. And there's a fingerprint on the certificate as well. The fingerprint is the fingerprint of the public key. And that's a very simple measure for you to see that it wasn't tampered with, that not somebody else tried to change the certificate between I sent it to you and you received it. Now, a certificate in this way is not really very useful because anyone can generate a certificate. In fact, I did in the previous demo. I showed you localhost 9001 and we saw that there is a TLS-based connection, and it was based on a certificate with my public key, but I created the certificate myself. That's not really useful yet. So a certificate also contains the name of the issuer, the party who issued the certificate, a signature by that issuer, and a signature algorithm is just a mathematical formula that computers can use to verify the signature. So how does this work, signatures? Well, public-private keys to the rescue, once again. This time it's a little bit bigger picture, but let's just go through it. In the top, we see someone who holds the private key. Am I saying that correctly? I have a bit trouble to see it. Yeah, it's the private key. So once again, it's my key. It's the key that only I have. And I'm writing a letter to, well, doesn't really matter to whom, and I will put it in the safe once again. And I'll use the private key to lock the safe. Again, the safe is now closed. We can put it on a truck, can be a very unreliable transport mechanism. And to whoever I send the message, well, they can be in the possession of my public key, because my public key is for each and every one in the world, remember? So everyone who sees the message has the public key and is able to open the safe. And by the fact that the safe opens and you can grab the letter out of it, you know that the letter is genuine and that it is indeed signed by me. That's a very basic principle. Now, how does this prevent us from non-genuine certificates? Well, there's an attacker there. You can see it's a pirate. He has an eye protection lab. And he has a different private key with a pirate on it. Now, what if he uses the safe, this very same safe, the same safe is just a mechanism, puts a letter in it, closes the safe. Now, the safe is shipped to any one of you, and you are holding my public key. Will the safe open? And the answer is no, the safe will not open, because it was locked using a different private key. And by the fact that you use my public key, try to open the safe and the safe doesn't open, you know that the letter was not signed by me. And you know that you should not trust its content. In reality, of course, you can still read the message, and it is your responsibility to verify the signature afterwards or before, whatever your choice. I go for before, by the way. But this is just an analogy, an example to illustrate how it works. So, again, a little bit of math. A signature is just a mathematical relationship between a message, a private key, and a public key. And the mathematical relationship has two functions. It has a signing function. The signing function is used by the person who wants to sign a message. It will give this function the private key that only he has and the message, and the function will give a value which is called t in this example, and t is the so-called signature. It's just a number, or basically a bunch of numbers. Now, if any of you wants to verify the integrity of the message, to see that it was indeed signed by the person you'd expect it by, you invoke the other part of the signature, which is the verifying function. You give the verifying function the message itself, x, the signature that comes with the message, T, and the public key. And if you invoke that function, you get either accept or reject as a return. Can be 1 or 0 if you prefer. But the thing is, invoking this function tells you whether it is correct or not. Given the message X, given the signature T, knowing the public key, we can easily verify if the message was signed using the corresponding private key. So the only thing that we're left with is a way to, well, generate some order of trust, to sign certificates by someone that we all trust. That kind of people or organizations are certificate authorities. A certificate authority is a company. Most of the times it's a company, but sometimes it's a non-profit organization like Let's Encrypt, which issues digital certificates, the certificates that we just saw, and these certificates certify that someone owns a public key and that someone is indicated by the subject. So to restate that, the certificate authority certifies that I own a public key. And by definition of this mathematical relation between the public and the private key, you can be sure that the corresponding private key exists and must be in my possession. It's my responsibility, on the other hand, to ensure that I'm the only one. If I put it on the internet, well, it's not private anymore, and I should basically revoke my certificate, because the certificate is your proof that using this public key, you can interact with me in a safe manner. So what happens there, basically, is this. There's someone there in the room. I don't know who you are, but it doesn't really matter. Because I know a person who's called John, and I trust John. John knows Alice and trusts Alice, and Alice knows and trusts you. And by the definition of trust, well, trust is a very, there's no compromise in there. By the definition, I know I can trust you, although I have never met you. That's awesome. Because we just need to know and trust John. That's all right. Easy one. But who's John? On my Mac, there's 169 Johns pre-installed by Apple. So I think John equals Apple. And if you don't have a Mac, don't worry. On Windows systems, it's just about the same. John equals Microsoft. And if you run Linux and you're like, haha, I'm secure, well, John equals Debian, or John equals Fedora, or John equals, well, Red Hat. Fedora is Red Hat is IBM, right? So what happens here, our systems and also our Java runtime environment comes with a pre-installed set of root certificates, system installed, and there's around 170 of them, which is quite a lot. Did you ever scroll through this whole list and make sure that you trust each and every one of them? I'll be honest, I did not. Many. Well, I think that's an understatement. But the good news is certificate authorities are very secure companies or organizations. And well, of course, they also have keys, public and private keys, because they need to sign certificates, right? And what they often do is they have a root certificates. That's what we just saw, the 170 of them, and they use those root certificates to generate intermediate certificates, which have a bit higher turnaround time, usually just a few years. But because they're signed by the root certificate, they can be trusted by thousands of computers worldwide, millions of computers even. The only thing is that every now and then, every 5 or 10 years maybe they need to rotate their keys. That's just a a good practice in security environments. Don't use your keys for too long. And if they do that, that's what they call a key ceremony. And a key ceremony is a very boring thing to attend. How do I know? Well, because these companies want to be open and transparent, so they publish a script of how the key ceremony should work. It's an 8-page document that starts with open the safe, get out the hardware that holds the crypto keys, and that ends with putting it back in the safe and locking it. But there's tons of things involved. Notaries are there. People from the company are there to just witness and to just have a copy of the script and check that every step has indeed been performed according to the script. They might even invite people from the street just to make sure that no one was bribed into, yeah, step 3 was indeed performed, but it wasn't. And if you pick some random person from the street, well, they can't be bribed before to collaborate in the process. They'll also keep a logbook of how everything went. They'll write down each minor derivation from what they expected in the script to happen. And they'll ask the experts in the room, do we all agree that we can derive from the script here? And if everyone agrees, they'll say, okay, derivation agreed upon. This logbook is published. They have cameras in the room, maybe 6 or 8 cameras in the room that will record everything that happens, and you can watch these videos. I did. Again, it's boring because it is an 8-hour video of people sitting in a room, sipping their coffee, checking their list, discussing stuff. Really, really boring. But, well, the good part is these companies have their security in place, right? Right? We can do a little fairy tale now. Some fairy tale. Who knows this picture? I'm in the Netherlands this time. This is one of the first times that I'm doing the talk in the Netherlands. Beverwijk. Awesome. This is Beverwijk. I've never been there, to be honest. And once upon a time, there was a notary that lived in Beverwijk. And, well, this digital certificate business was pretty booming, and I thought, well, that's basically what we do already in an offline world. We could do this in a digital world as well, and we'll make a bunch of money there. So they started a spin-off, which they called DigiNotar, and it lived happily and carefree in the town of Beverwijk. But on a bad day, an attacker found their systems. And he found that their website was running .NET Nuke software. I'm not saying .NET or .NET Nuke is bad. I'm just observing that it ran .NET Nuke software. A very specific version, 4.8.2.0, running on a machine win SRV 190. But this version of .NET Nuke has a file upload vulnerability. And that was widespread, widely known already by that time. I'm giving these details, by the way, because it's in the forensic report that was published after the fact. Now, using this security vulnerability in the file upload function, the attacker was probably be able to compromise the passwords of the aforementioned WinSRV 190. And due to the fact that, well, it wasn't very strong security that created those passwords, very strong security policies. And the company actually had the domain system, the domain admin password on the very same system. The attacker was able to enter the network of DigiNotar and traverse through their infrastructure, server by server by server, using this administrator password that he had found to finally reach the core of their business, the machines where the keys and the certificates lied that were the root of DigiNotar's business. What does this mean? Anyone? Shortest summary I've ever had. Trust, boom. Exactly, longer version, but also as correct as the previous one. Anyone can now pretend to be anyone, or at least the attacker can pretend to be anyone. So what happened in the days thereafter? Google gave an update of Chromium, blacklisting 247 certificates that had been issued by DigiNotar. Microsoft removed the DigiNotar root certificate from all their supported Windows releases. Mozilla revoked trust in the DigiNotar root certificate in all supported versions of Firefox, and Apple issued a security update which basically removed the same root certificate. Note that small asterisk over there. This is your moment not to be proud to be Dutch. Because what happened? One of the customers of DigiNotar was the state of the Netherlands, the Rijksoverheid. And they thought, well, all our internal systems use certificates issued by DigiNotar. So if we are rolling out this update through our whole government infrastructure, none of our people can do their work anymore. This is a big issue. And they asked Microsoft, well, it's perfect that you issued this update, but could you please withhold it for the Netherlands for a few weeks? We need to fix a few certificates first. And Microsoft did that, because they're very helpful in such cases. So in fact, things got worse, because the main part of the DigiNotar customers, obviously, were Dutch customers. It was a Dutch company after all. And for the Netherlands, the update was delayed, intentionally. And to make things even worse, the responsible person in the government said, no worries, just check the green mark there in your address bar. Right? It's as if I come home someday. I look under my doormat and think, well, there used to be a key there under the doormat. I think somebody found it. Ah, that sucks. But wait, tomorrow the house cleaner will come. She needs to be able to get in the house, so I'm not yet replacing my door locks, because the house cleaner needs to be able to get in and I'm away. So I'll delay that for 1 week. Well, what do you think that the person who found the key will do in the meantime? They're not going to wait for you. So, very shaming moment, and as I said, this is not your moment where you are proud to be Dutch. But, well, it happened. We can't change that. What happened eventually was that DigiNotar updated their certificate revocation lists. Certificate revocation lists are lists published by every certificate authority that describe, well, we issued a certificate in the past, but in the light of today, you shouldn't trust it anymore. Well, they should basically do that for all the certificates that they ever created, obviously. But, well, it was a bit after the fact, because no one trusted their root certificate anyhow, so what doesn't really matter. So, once again, time for a quick demo. Because what have we seen so far? We have seen how you can be sure that some certificate containing a public key presented to you is indeed secure. Now I have a web server on my machine which listens to the address demo.google.com. A different port, and only on my machine demo.google.com exists. Don't worry. Welcome to Google, it says. And wow, it seems to say that I'm indeed talking with Google. But you all know this is not the case. How can you, what trust do we have right now? The trust that we have right now is that we can be sure that we talk to the machine that we think we're talking to. What we cannot be sure of is that this machine is indeed in the possession of the company that we think we do business with. And to address that, certificate authorities created a new type of certificate, which is called an extended validation certificate. And you sometimes see that. Make it a little bit smaller. The first example that I know of is ING. This little part there says not only the certificate is valid and this is the corresponding key material, but it also says we, the certificate authority, issued this certificate to an entity, a legal entity that we identified in the Chamber of Commerce as being ING Bank NV in the Netherlands. And this is the trust for you that you are indeed talking with ING in this case. It's not the HTTPS and the green mark, because if you would have made a typo and you would have typed ign.nl, I registered that one. And I requested a valid certificate for ign.nl. And I created a website that looks just like the one of ING. And you think you're talking with ING, but you're talking with me. And I also created the login screen of your internet banking environment to look just the same. You get the idea? You're not talking with ING, you're talking with IGN, which is somebody else. But this, the extended validation, proves to you that you're indeed talking with, in this case, your bank. The disadvantage of extended validation certificates is very simple. They're pricey. They're a lot more expensive than regular SSL certificates, TLS certificates, excuse me. Especially if you compare it to, for example, Let's Encrypt, because they give you a certificate for free, like €0. Well, always more expensive. Anyway, last section, and then we can move on to the opening of JFOL, is a quick walkthrough of the tools that we just saw and some tips and tricks. First of all, I've used CURL quite a few times. If you supply the -v switch, it will give you verbose output, so it will tell you the HTTP commands that go over the wire. If you supply -k, it will also ignore certificate validation checks. Why would you do that? Well, if you see that you can't build up your trust yet, you want to be able to inspect the certificate and see if it's the certificate that you expect and by whom it is signed, etc., etc. So then you give the -k switch, otherwise you don't. Then you give an address, and CURL will then just do a get or a post or whatsoever. If you need to troubleshoot trust certificates even further, you can use the OpenSSL toolkit. It comes with an sclient command. If you supply show certs and server name with the address that you're trying to connect to, and then say -connect address :port number, you'll see each individual certificate that goes over the wire. And you'll see a lot of input then. If you have issues with supported ciphers and protocols and compression methods, we didn't even go in there today, but in case you have the feeling, the gut feeling, well, it might be something with ciphers that's not going correctly, use the nmap tool. It has a SSL enum ciphers script. You give it a port number and an address, and it will just dump out, okay, the server says it supports the following ciphers. The server says it supports the following protocols. It says it supports the following compression methods, etc., etc., etc. And you can easily try to match that with your client and see if there's a mismatch, probably. If we're on a Java conference, so how does it work in a Java environment? I think we've all seen this one. Javax Net SSL Trust Store is a system property that should point to a file. The file is a trust store, and a trust store is just, as it says, it's a store where we can put the trusted certificates in. You can protect such a file with a password. If so, you also give Javax Net SSL Trust Store password. The password to the default trust store that comes with the JVM is a suggestion. Change it. So, there's also corresponding settings for a key store. This can be a different file. It can also be the same file as the trust store. The key store is a file that contains private keys. So if you use, for example, mutual transport layer security, where you also need to supply a client certificate, this is where the key pairs go in. And also there, you can protect it with a password. Now, you've pointed to the correct trust stores. They only contain the certificate authorities that you trust for this specific system that you're building today, but it still doesn't work. Well, then you start your application using Javax Net Debug. And if you give the value SSL, it will give you tons and tons and tons of output, like a lot. more than you can handle probably, more than I can handle at least. So you can filter that out a little bit by supplying a flag there with a color, and these are the flags that you can use there. For example, well, I have the feeling that it's somewhere in the handshake. Well, just forget about all the rest, I just want to see the handshake stuff. If you want to change, update, see a trust store or a key store, the JVM comes with the key tool command, which is, well, not the most user-friendly experience I've ever seen. It's a very complex command line interface. But there's also a graphical user interface for that. It's called PORTECLE. It's free and open source available. And well, you can just click around, inspect the certificate, see what's in there, see the keys, see when it expires, who issued it, etc., etc., etc. And with that, we've come to the end of this talk. If you have any questions, shout now, or find me on Twitter. Username is down there. You can find me at the InfoSport booth, and I see there's at least one question. Please shout. Yes? The question is, what happens if I delete all 169 certificate authorities on my MacBook? I go to Facebook, and Chrome says, connection not secure. I go to a Mac update, to the App Store that contains Apple updates. It says, no secure connection. Can you rebuild it? I think you can. I've never tried it. I'm a bit afraid that I won't succeed. But on the other hand, if you are building systems with high security requirements, you could create an empty key store for your Java virtual machine running in OT HRP environment, and give it an empty key store and just add, for example, the root certificate of the certificate authority that you know signed the certificates for the system that you're talking with. There should be one, and only one of them. Well, if they ever switch CAs, they should tell you. If someone sits in between and tries to intercept the traffic, your system will not work anymore, but that's what you want because someone is sitting in between, and you don't want to trust the connection anymore. Does that answer your question? Great. Any other questions? Yes, please.
Yes, you said that our government was basically cutting their pants down when the DigiNotar certificates were all revoked. Well, let's assume that they couldn't know beforehand that this was going to happen, but would it have been possible for them to use multiple certificate authorities so that if one of them were to suddenly no longer be trusted by anyone, they wouldn't get into this kind of situation?
Good question. Is it possible to avoid these kind of troubles by splitting your risks over multiple certificate authorities? Well, technically, a certificate is Technically, a certificate is always signed by one CA. So what you can do is for each and every system that you're building, generate 2 certificates and have them signed by different CAs. It's going to be expensive, but you can do that. I think that the current PKI overhead initiative is not exactly doing that, but what they are doing is that they are splitting their risks, because PKI overhead, I usually pronounce it in Dutch, so having a bit of trouble there. There's not one party who does that. There's, I think, 4 or 5 companies who can, on behalf of the government, sign certificates. And I think they did that, especially to cover these kind of issues. If one of them goes bankrupt, if the other one is compromised, it's no problem at all. We have 2 left. Does that answer your question? Yeah. Great. Yes, please.
I've also often noticed that when you're, for example, discussing security, like we need to have certificates, they always talk about SSL.
Yeah.
We've just seen in your presentation that you should use TLS.
Yep.
So are people actually using the wrong words when they're discussing actually certificates and security?
Are people using the wrong words when they say we need SSL? I think it depends. I think many people, especially those who are not really well educated in this matter, will just use SSL and TLS as if these are synonyms for the very same thing. If you're talking with a security expert, a penetration tester, a infrastructure tester, and he says SSL, big red warning flag. No, we're not doing SSL anymore. We've skipped that like 10 years ago. We're now on TLS, right? And if he says, I don't know what you're talking about, find a different person. If he says, oh yes, of course, you're right, you're good to go. But for example, many security officers, well, they don't exactly know the exact details, but they just know we need to have secure transports. And they name that SSL, but what they mean is TLS, oftentimes. Okay, it's 8:55. Thanks all for your attention. Have a wonderful JFOL.